Hello everyone, this is on our standard normal distribution, which is our chapter 6 lesson. It's the first lesson, and we're going to talk about the standard distribution, and this is a very important concept of our statistics course. The standard normal distribution has three properties. One is that its graph is bell-shaped, and we've all heard the normal curve, the bell shape, that sort of thing in terms all over the place. Its mean, we know what the mean is always equal to 0. That means the mean is going to be in the center. You'll see this mu symbol with a Greek mu, meaning mean of the population, is equal to 0. The standard deviation is always equal to 1. Sigma equals 1. You need to develop the skills to be able to find the areas or probabilities, area, probability, the exact same thing, of relative frequencies, which correspond to various regions under the graph of the normal distribution. We need to find z-scores that correspond to the area under the graph. Well, what we're talking about, just giving you a quick, brief graph here, is the normal curve. And we're stating that right down the center, mu is equal to 0. We're also saying that we're going to be finding what's called z-scores. Well, z-scores are going to be here along the x-axis. So my z-scores are my x-axis. My relative frequency is going to be my y-axis. Well, the z, keep in mind, on the x, if 0 is here, if I go to the right, we know that, of course, on a regular number line, it continues to go up in positive numbers. If I go to the left on any number line below 0, it's going to be negative numbers. And that's the same thing. That's our actual z-scores. So we also have something called a uniform distribution. A uniform distribution is where there really isn't any change or very little change in the values. They're evenly spread over all the probabilities. For example, if I were to have a distribution of rolling a die, we all know that if I roll a die, each side of the die has 1/6 of a chance of being the number that's rolled. So I would have a normal distribution with the numbers 1, 2, 3, 4, 5, or 6, and that distribution would all be the same as 1/6 of the probability. A density curve is really the graph that I just drew. It's a continuous probability distribution, and under that is got to have a total area of equal to 1. So again, when I have this density curve, the area under here, under the curve, is equal to 1. Every single point on the curve has a height somewhere between 0 and 1. It can't be any more. We know that probabilities can't have to be between 0 and 1. The nice thing is that when we have to learn how to find the area under the curve, normally we would have had to use calculus because calculus tells us how to integrate to be able to find the area under the curve. But we're going to be able to use technology and tables that we have at our disposal to find those areas. So this is a normal distribution, and this particular one is about waiting in line at the subway. Well, because of a normal distribution, that means waiting for 1 minute or 2 minutes or 3 or 4 or 5 minutes all have the same probability. And you can see here it's 0.2. 0.2, as we know, is the same as 20%, which also is the same, I could write that as a fraction, as 1 1/5. They all mean the same thing. So given this particular problem, given the uniform distribution illustrated here, find the probability that a randomly selected passenger has a waiting time greater than 2 minutes. So I'm going to get my highlighter out. So greater than 2 minutes. Well, here's 2 minutes, and greater than would be this whole area. The whole area is equal to 1. So I know it's got to be less than 1. So I've got to find out how to find the area. Well, let's think about this. We also know that to find an area of a rectangle, the area is equal to the width times the length. We know that from elementary school. So we've got to put some idea of what's going on here. Well, we know that the distance from here to here, we are given that to be 0.2. That's also now going to be my width of my rectangle. Because I know my area has to be 1, that means that 0.2, which is my width, times L has to equal 1. And we know from algebra class that dividing by 0.2 is going to give me my length. And of course, I can just go into the calculator and make that division and know that 1 divided by 0.2 is 5. And guess what? That's exactly what it tells us here. The entire length is 5. So to find the area of the shaded region, we're going to figure out that it's 1, 2, 3, 3 times the width, which is 0.2, and of course 0.2 whoops, I'm grabbing the wrong thing here. The area is equal to 0.6. And of course, we want to keep in mind units, and that area is referring to what? The probability of waiting 2 or more minutes. So here's a picture of the normal standard deviation, or sorry, standard curve. Please note this is exactly the picture we looked at earlier. You'll see that here's my z-score. My z-score is exactly in the middle. My z-score is 0 because mu is 0. And everything in the normal distribution right now has a mu of 0 and a standard deviation of 1. When we get to the next chapter or next section, we're going to be talking about things that might have a different mu, but we can still call what's normalizing the scores by assigning them a z-score. So the normal distribution, again, the area is equal to 1. There is a definite correspondence between area and probability, and they are exactly the same thing. So there's several ways that we can find this area under the curve. We can use our table, and we can bring up the table and talk about how to use that. We could also use Excel, StatDisk, Minitab. The one that you're going to use most often, of course, is going to be your TI-83, 84 calculator. Let me pull that up so that we have that ready. And you can go get your TI-84 calculator if you do not have that ready. I'm also going to bring up the table. Now the table is in your textbook. However, you can also get it online on your online. This is what the tables look like. We're not into binomial. We're not doing binomial at this point. We are looking at z-scores. I just want to go over how quickly to read these z-scores. Here's our z. These are the negative z-scores. And as you go across, you're going to see and down. So with a z comes as 2 decimal places. And if I were looking for negative 2.63 as a z-score, I would have to go to my column here and look down, and as I'm looking down, it's not giving me my highlighter capability here. I'm going to look at the row that says negative 2.6, and I'm going to go all the way over to the column that says 0.03. So now I have negative 2.63, and when looking at this chart, I can see my z, my area under the curve, is 0.0043. Now keep in mind that means the area under the curve from all the way out at the very far end of this tail to where z is negative 2.63. The area is 0.0043. Keep in mind that the table consistently will give you the area under the curve, whatever z is. It gives you the area from that point to the end. That's how that table reads. Sometimes we don't need that area. Sometimes we have to do some work to get the area we need. Okay, let's see if I've got my calculator has loaded. Okay, now that I've got my calculator loaded, I can use the calculator to find the area under the curve. The way I'm going to do that using this problem, because I want the area from the very far left-hand corner up to where z is negative 2.63, I'm going to go to second vars or distribution. I'm going to come down to the normal curve distribution frequency. Choose that. Now on my 84, it's telling me and giving me prompts. And it says negative 1 to the exponent of 10 to the 99, which means it's going to be 0.000000 all the way down to 1. So it's going to be so significantly small. Those of you who have to punch in exactly what it is, I'm going to show you what to punch in. You should punch in negative 99999 That's my lower end because it's the low all the way to the very end of that normal curve. Then I'm going to cursor down. Those of you with the other software are going to put a comma, and on the upper I'm going to type in negative 2.65. I'm going to cursor down. Those of you on the other screen are going to type a parenthesis to close. I'm going to click on paste, and now both of our screens should look exactly the same. If you don't have 0, 1, that's fine. It'll assume that it's 0, 1 anyway. So now go ahead and press enter, and we used the table and we came up with 0.0043. This is just a tad bit different of 0040. So we talked about using that table already. We just want to make sure that you understand that there is one page for negative z-scores and there's another page for positive z-scores. So I can bring that table up again. So there's my negative z-scores, and notice that it shows me that they're coming from the very end to z. On the next page are the positive. Notice that positive have to be greater than 0. Well, that just makes sense to us. Positive have to be greater than 0. Keep in mind that z-scores can be positive and negative. Areas can never be negative. You cannot have a negative area. That just doesn't exist. Notice here at z is 0, 0, 0, right at 0. The area under the curve is 0.5 or 1/2, and it's exactly 1/2 because you're cutting that density curve directly in half. If I look at a probability or a population distribution, that's a normal curve, 50% of my population are going to be up to the mean and 50% are going to be higher than the mean. So here's an example, a bone density test. That bone density test is a mineral test that helps identify the presence of osteoporosis. The results of the test is commonly measured with a z-score that has a normal distribution with a mean of 0 and a standard deviation of 1. That's exactly what we're studying, the normal distribution. A randomly selected adult undergoes a bone density test. Find the probability that the result is a reading less than 1.27. So you're going to hear me say this a lot. Draw it, draw it, draw it. So I'm going to sketch this graph of the normal curve. There's where my mu is of 0. We know that 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. There are also my z-scores, and of course I could do the other side and go the other way of -1, -2, and -3. But I want to find the probability that the result is less than 1.27. So I have to think about first, where is 1.27? Well, obviously 1.27 is a positive number. So 1.27, and you're just sketching, so 1.27, I'm going to write it's right about there. That's my z-score. When it says I want to know the probability of having it less than 1.27, let's get that highlighter back and we're going to shade the area that we're looking for the area of. And that's this area because that's less than 1.27. So this is where we use our chart or we use the table or a calculator. So pulling up our chart, is a positive z-score. The positive z-score is 1.27, so I'm going to go down my column here of 1.2. I'm going to come to 1.2. Then I'm going to come all the way over on that line till I get to 7. So it should be 1.27, which is 0.8980. So 0.8980. My pen will not write. So we found that the area under the curve was 0.8980. That's an 8, not a 9. So let's just check it out on our calculator. So turning that back on, I'm going to go to second distribution, and I'm going to go down to my normal density curve, negative 9999. It's from the far down to the left, and I'm going up to 1.27. Going to cursor down and say paste. Again, you're going to, if you have the different operating system, put that in parentheses, negative 99999, comma 1.27. Close your parenthesis and hit enter, and I get 0.89795, which of course would be rounded to 0.8980. So the probability of selecting a person who has a bone density reading from the test less than 1.27 is 89.8% or almost 90%. I'm going to do the same bone density test here and find the probability that a randomly selected person has a result above -1, and that's still to be considered normal in the bone density reading. So let's find out how many are in the normal range for bone density. So let's draw a curve. Always start with drawing the curve. Take the time to make that sketch because a picture says 1,000 words. That's 0, -1.0. And it says I want to know the probability when they're above 1, -1. So I want all of this area. Now, if I go to my table and I look for the area under the curve where z is -1, it's not going to tell me the area that I have highlighted. Instead, it's going to give me this area. So let's just go look at that. So this is a negative z-score, so I'll go to the negatives. And I'm looking for -1, 1.0. 1.0 is 0.1587. It will be right there. 1587. That's what it's giving me, the area from the end to Z. But I want the other area. Well, that's easy to figure out because I know the area under the curve has to equal 1. So I have 1 minus out this area that's left. When I do that, I find that this area should be 0.8413. So you can see by drawing and sketching, it helps you realize where the area is and what you need to do to find it. So let's go to our calculator. And again, we're going to go second distribution, cursor down to normal. This time our lower end is at -1.0. Our upper end, we can just put in some 9s and enter. And it's 0.8413, exactly the same we got using our table. So now it says I want a bone density reading between -1 and -2.5 because this indicates that the subject or the patient has osteopenia. So again, that little sketch doesn't take time long to do, but it really does help keep things where they should be. Well, I want negative between -1 and between -2.5. So here I've got to be here, -2.5. So keep in mind when I go to my table again, if I were to use my table and I'm looking for -2.5, when I find -2.5, the area it's going to be talking about is from this very end, and it's going to be this little tail. So -2.5, it's 2.50, so it's 0.0062, and you can see that on your table. Now I need to look up the area from the end to -1. We never shaded our area, so let's go back and just shade that little area that we want. So I'm going to use that table now to look up z is -1. Well, z is -1 is right here. -1.0 is here. So that is 0.1587. And that's the area for this whole thing. So to find the area that's left over, yes, I've got to subtract 0.1587 minus 0.0062. And I get this area that's highlighted here, 1525. Now that's a lot of work, I get it. But again, you could do that on your calculator. We're going to go to our second distribution, our normal distribution, go down to number 2 there. My lower end now is going to be -2.5. So again, you see how critical it is just to draw that curve. My upper is -1.0. I'm going to cursor down. You're going to close your parenthesis and hit enter, and we're going to get 1525, which is exactly what we got using our table. Notation. Notation is here, and it notes that the probability that the z is between A and B. That's just like the one we just did. The probability between -2.50 and -1. This denotes that I want the z is greater than, and z would be less. Denotes the probability that z is less than the A, where we could shade the table to be either greater than or less than A. So here again is finding the z-scores from known areas. First, I'm going to draw the bell-shaped curve and identify the region of the curve. So now from a known area, finding the z-score, we're really just going the opposite way. We're going to be looking in that chart for the area and then finding the z-score that coordinates with. Okay, so let's look at an example of finding the z-score given the area. So here we have an example of finding the area that's under the curve. Here it is. It's telling us it's 0.95. And It's the same thing as finding the 95th percentile, because 95th percentile would mean that 95% of the people were at that level. So what's left over if I have a 95 percentile? Well, there's only 5% or 0.05. So I've got to find that z-score. So let's pull up that table. We know it's going to be a positive z-score, so on our table, we're going to go to positive z-scores. And we're going to look and look and look until we can find the closest to 0.950. So I'm seeing here 0.9484, 0.9495, 0.9505. Well, it's exactly in between. So this is the one time, because it's exactly in between, that 0.95, we're going to go in between those two z-scores. You can go back here and look. 1.64 and 1.65. So our z-score for 0.95 area, the z will be 1.645. And that's a special case when it lands exactly in the middle. If it wasn't exactly in the middle, you would just pick the one that is the closest. So here we're going to use that same bone density test, and we're going to find the bone density scores that separate the bottom 2.5% and the top 2.5%. So here we go. We're going to do that sketch again. You know you're going to be sketching these a whole lot. As a matter of fact, I have put some up that you could print out and just go ahead and write on, just to make it easier. So remember our zeros in the center, and I want to find the bottom 2.5 and the top 2.5%. Well, 2.5% isn't a whole lot. It's very small, so we're going to put some z, that's what we're finding, and some z here, remembering that my area, this little bit, and this little bit, is 2.5%. But remember, when I write 2.5% as a decimal, it's going to be 0.025. 0.025. So I'm really looking for the z when the area is 0.0250. So I'm going to go to my table, and I know it's going to be a negative z. So I'm going to look here for my areas, and I'm going to find that here's 0.025, but that's not what I want. I want 0.25. Here's 2.2. Here I have 0.0250 right here. That is what I want. So I'm going to look to know that it's negative 0.196. 0.196. Well, because this curve is completely symmetrical, in other words, if I folded it right here on the half, the other half would be on top of it. So this is going to be positive 1.96. So lastly, we're going to find a definition here. And critical value is a z-score separating unlikely values from those that are likely. We've talked about likely and unlikely values before. The notation that we use is the expression z with a little a at the bottom, and that denotes the z-score with an area of a to its right. So be very careful. It's the z-score and the area is to the right. It's not what our table gives us. Its area is to the right. So find the area or the value of z at 0.025. The notation z at 0.025 is used to represent the z-score with an area of 0.025 to its right. Refer back to the bone density example. So if we do that, we'll remember that we have our normal curve and 0.025. Think how small that is. That's a teeny tiny, that's like 2.5 cents of a dollar, teeny tiny. And we want the area to the right of z. Well, that means right is this way. So it's going to have to be this little area down here, and that area has to be 0.025, this little area. And just a few minutes ago, we did look in our table and we found that to be 1.96. So obviously there's going to be a way to do that on our calculator. I'll bring my calculator over now. Let's go to our distribution again. So second distribution. We're going to go to normal. Cursor on down one more, and now we're going to do inverse of the normal. So I'm going to be able to put in the area, and it's going to give me the z-score. So it's the absolute inverse. So here's the problem. It wants the area, the same as the table, from the other side, from the left going to the right. Again, we're going to use the fact that we know the entire area is 1. Since my entire area is 1, I'm going to subtract away 0.0250 to find the area here. And of course, when I do that, I'm going to get 0.75. So the area here is 0.75. So on my calculator, for my area, I'm going to, that's completely wrong. Got to subtract correctly. Trying to use money and quarters, huh? So here I'm going to get 0, I'm going to get 5. Obviously, I'm going to have 9 minus 2 is 7, but I can't forget to bring down my what? My 9, because I had to borrow. So I know the area from the very left-hand side onto my z is 0.975. And I'll have that there. Those of you that have the other one, you'll just close your parenthesis, and I get 1.959, which really is the same as 1.96. So just for practice, let's go back a couple here. So we can use the calculator. Here we had the area from the end to be 0.025. Again, we're going to use second distribution. We're going to come down to inverse. We're going to put the area in a 0.025. And enter, and we find it's negative 1.956. So here's some examples, so we'll have some more practice. Here we're still using that mean of 0, a standard deviation of 1. We're going to draw a graph and find the probability of the given scores. So here we have less than negative 2.04. There's my graph, 0. We know negative 2.04 is going to be way down here on the end, and I want to find the probability that it'll be less than negative 2.04. Again, I have the z-score. Don't get your z-scores in your areas confused. I have z, I'm looking for area. So I'm going to go to my distribution and say normal curve. I'm coming all the way from the end. This is where you can put in negative 99999. My upper limit is negative 2.04. I'm going to put and enter, and I find my area is 0.0207. And of course, then again, if we highlight that area, it's that little teeny area there. So think about this for a second. My next one says less than negative 0.19. Less than negative 0.19. Think about that. Is the area going to be, or the probability going to be more than when the area was, the z was negative 2.04, or will it be more? I know this is where students get confused a lot of times. So if I draw my normal curve, again, picture says 1,000 words, that's 0. Well, negative 0.19 is really close to 0, isn't it? So it's going to be really close here, still negative, and I want the area that's less than. So again, we can highlight that area. Again, we can go to our calculator, to our normal curve, and I'm going to put from the very end negative 99999 to negative 0.19. That's my z. Again, I'm looking for area, and enter. And I'm going to get that that area is 0.4247. Sorry, my pen went kind of wacky on there, but it's 0.4247, and that makes sense because we're real close to the 0, so it should be real close to 1/2. Let's do at least one more of these. Let's do number 29. Just draw my curve. That's 0. And I want to be between negative 2.2 and positive 2.5. So if I were you, I'd pause the video and see if you get the correct answer. I'm going to keep on going. Well, I know that negative 2.20 is going to be here, and positive 2.5 is going to be somewhere up here, and I want it to be between, so this is the area that I'm interested in. That's a big area, so I'm beginning to think that the answer I should get should be pretty close to 1 because I don't have much on either end left. So I'm going to go to my calculator, second distribution. Going to go down to number 2, normal curve. This time my lower level, my lower limit, is going to be negative 2.2. I'm going to cursor down and make my upper limit as being 2.5. I'm going to cursor, get down to paste. You guys are going to close your parentheses, hit enter, and it is very close to 1, just like we thought it would be. 0.9798 is 0.9799. So let's practice here. This time, we're going to look the opposite direction. Remember, our notation says z of 0.01. It means that z score with the area to the right is 0.01. Well, if we have an area down here, it's 0.01. It's got to be very close to the end, doesn't it? And I'm looking for area. So remember, on my calculator or my table, it's this area that it's going to be referred to. Or remember symmetry, and I could really look for negative 0.01 or put that into my calculator, and it would be the same area on both sides. So second distribution, and I'm going to do the inverse norm because now I have the z-score. I'm looking for the area. This is another important reason to remember that z-scores are only 2 digits. Area is 4. Do not get them confused. So I'm looking for the area right here or right here. And give me that z back. So it's point. And that's going to be a negative 2.33. So this z-score is negative 2.33. This z-score is going to be positive 2.33. That concludes section 6.2, which is the introduction to the normal curve.